Hello, my name is Iakovos Tzokas, and I'm honored to share the findings of the picosecond test facility at UTA under the direction of Dr. Brandt. Specifically, I would like to present our novel pixel-based accelerated aging detection method using the large area picosecond photodetector, or LAPPD, developed by Inc. In particle physics, detection of individual photons is of paramount importance, so physicists use devices such as the one shown here, a microchannel plate photomultiplier tube, or LAPPD, provided by Inc. Figure 1b shows how a photon couples to an electron, which leads to the release of a photoelectron at the photocathode. An electric field drives the electron towards the MCP, which allows us to multiply these electrons, with figure 1c being an expanded depiction of this process. Due to the avalanche conversion, which leads to the multiple production of electrons being collected at the anodes, gives us an evidence of the original photon. Quantum efficiency, or QE, is the fraction of photons that produce an electron. In practice, corresponding positive ions from the MCP move to the opposite direction, which in turn damages the tube and impairs its QE. This process is called ion feedback. It is the main cause of MCP gain degradation and loss of QE. Positive ions that collide with the photocathode at high energies cause more electrons to be triggered and an afterpulse to be detected, as you can see here in figure 2. Although today we'll be talking about the pixel-based accelerating method that we use in our lab to test the lifetime and its referred ion feedback. The lifetime testing, as we know today, exposes the entire active area of the detector uniformly. Although exposing the entire active area of the MCP-PMT during the lifetime test renders the entire device useless for future testing. What we propose is a pixel-based accelerating lifetime test method where a localized area of the tube is exposed to higher event rates. With this, we hypothesize that the damage due to the radiation effect is highly localized and global effects are limited, and also we showed that the accelerated method is viable as the ion feedback is dependent only on the first MCP. Here we see the experimental system. In this case, we have the irradiation system, which is where we have a laser which passes through some NDF and then to an optical fiber. That the optical fiber goes to the detector. And here is the second testing, where we see where we measure the quantum efficiency of our detector. Here is how the quantum efficiency is being calculated from the different currents that are being measured. In this case, these are the heat maps that are being generated. This is the heat map before the irradiation, and this is the heat map after the irradiation. As we can see, the damage is highly localized, with the black being where the quantum efficiency drops to 0. As we can see, the pixel radiation is highly localized because this is where the peaks are, and if we do the fitting, we can see that at the fitting it's highly localized, and it's 2 millimeters as the ones that we suppose the size of the pixel is. The larger diffusion that we see, that is represented by this larger Gaussian, is dependent to the fact that due to the coating of the photocathode not being exactly uniform, we have that the quantum efficiency is not uniform of the area, so from the beginning, so that's why you have a larger Gaussian that is represented by this and this in the both x coordinates and the y coordinates. Here we can see what the charge extracted was as a function of quantum efficiency. Here we can see what the saturation behavior of the MCPs are. This is the 2 MCP saturation behavior. As we can see that the expected ratio is much higher than what the measured ratio is, while the expected ratio and the measured ratio for the single MCP behavior is the same, which means that there is a saturation. There's a higher saturation when there is 2 MCPs than when there is a single MCP, which means that there is only dependence. There is dependence of the afterpulse rate only on the first MCP and not the second MCP. So that's how the ion feedback is only dependent on the first MCP. So the conclusions in our future works are that we successfully showed that there is a highly localized damage of the LAPPD and the efficiency of the pixel-based accelerating aging technique. There is minimal damage surrounding pixels due to the internal diffusion of the laser light, due to the glass panel in front of the LAPPD. In the future, we hope to develop a theory to correlate ion feedback to lifetime of LAPPD by just looking at the afterpulse, and thus allowing us to not have to have a non-destructive method to measure lifetime. Thank you very much for your attention, and thank you.